Welcome back. This is video lesson 4, where today we're going to be talking about volumes of revolution. Let's get started. So previously in this course we saw how to compute volumes of objects that can be sliced into cross-sectional pieces. So let's review that. Here's an object. I have it like lying down along the x-axis. It looks like this over the interval from a to b. Okay, so this is just some arbitrary object, and over each point on the x-axis I have a cross-section which is some two-dimensional shape. So if, say, this is the point x here, actually, I'll draw that in a different color. If x is here, then I have a slice above x, which is some shape, and I suppose that I'm given the cross-sectional area at each point x as a function a of x. Then we've seen that in order, if I want to calculate the volume of this solid, I can just integrate a of x from a to b, and that gives me the volume. Okay, so this is what we're going to use to get to talking about volumes of revolution. The volumes that we'll be talking about today are made in this way, but from a fairly specific process. So the process is, I start with a graph of some function. So here's an example. Here's my graph of y equals f of x. And that lies over the interval from a to b. And what I'm going to do is take the region underneath. So here's the region underneath the graph. It's this two-dimensional region. And I'm going to revolve it around the x-axis. Meaning, imagine that now this two-dimensional plane that I have depicted here is inside 3 dimensions, and I can take the x-axis and spin it, and that takes the solid around the x-axis, and that traces out a 3-dimensional shape. So I'll attempt to draw that shape. So the object that I get here is sort of like a volcano lying on its side, I guess. Okay, so I want to calculate the volume of objects obtained this way by taking a region in the plane, in this case a region underneath the graph of some curve, the graph of some function, and revolving it around an axis. So this object is just like the one that we saw on the previous page, in the sense that we can think of it as broken up into slices, and to calculate the volume, all we need to do is figure out the cross-sectional area. So here's a slice in green at the point x. And the question is, how do we figure out the volume, or sorry, the area of the slice at x? Well, I took it, hopefully, if you stare at this picture long enough, you can convince yourself that actually that green slice is a circle, or it's a disc. It looks like this. So here I'm looking at it from the side of the solid. If I kind of arranged my view so that my eyes are at the origin and looking down the x-axis, I would see the green disc like this. So this dot in the center is where the x-axis intersects the slice. And to find the area, all I need to do is figure out what the radius is. And from the way we constructed it, this radius is exactly the value of the function at x. So we get that the area of the slice at x is the area of a circle with radius f of x. So that's pi times f of x squared. Okay? So this leads us towards what's sometimes called the disk method for finding volumes of revolution. So I guess I already said this. Each cross-section is a disk, and the cross-sectional area of each disk is the area of a circle with radius f of x, pi times f of x squared. And just like we saw at the beginning, to find the volume, I can just take the integral of this from a to b, and I get the volume. Let's do an example. So I want to compute the volume of the solid obtained by rotating the region under the graph of y equals x squared over the interval 0 to 2, and I want to rotate that region about the x-axis. So here's that formula again, which you can easily derive on your own, right? If you know the area of a circle, you can figure this out. So go ahead, pause the video now, see if you can figure out how to do this problem. I highly recommend that you draw a picture first and label the interval and try to draw a sketch like I did of the solid revolution, and then compute its volume. Okay, here's the picture. I have y equals x squared from 0 to 2. So here's 1. Actually, let me start this over. A little bit bigger. Here's 1, and here's 2. And then here's, if I'm looking at y equals x squared, it goes up like this. And this is not the scale, but at this point, I'm at 4. So this is 2 comma 4 right here. And I'm taking this region under the curve, and I'm revolving it around the x-axis. So I get something that looks like this. It's like a solid wizard's hat, I guess, is the object here. Okay, so that picture's not that great, but something I always like to do when I'm doing these problems is pick just an arbitrary point on the interval that I'm working over and draw in maybe a different color or highlighted, draw one of the typical slices, which, remember, in this case is a circle. So remember that the area of each slice at x is pi times the radius of this disk, right? And the disk is, this is the curve y equals x squared. The disk has radius x squared. So the area is pi times x squared squared, which is pi times x to the 4th. So to find the volume, I integrate pi times x, well, maybe I should write, just for now, pi times x squared squared dx. And the limits are from 0 to 2. That's the interval that I'm working over. So I can simplify this a bit. I get pi times the integral from 0 to 2 of x to the 4th. And this is pretty straightforward from here. I have pi times an antiderivative of x to the 4th is x to the 5th over 5. And I'm evaluating from 0 to 2. And so I get x to the, so 2 to the 5th is 32. You get 32 pi over 5. And that's the answer. So that's the volume of this solid object. Okay, so let's make things a little bit more complicated. Now I'm going to do the same thing where I revolve a region around the x-axis, but the region is going to be a little bit different. So now I have a region that's bounded above by some, maybe looks like this, the graph of f of x, and it's not, so previously it was the region was bounded below by the x-axis. Now I'm going to say I have some other region, some other curve, y equals g of x, that bounds my region below. So again, I'm going from A to B, and I'm taking this region here. Okay, well maybe I'll move my B over a little bit. And I'm taking this region and I'm revolving it around the x-axis. So let me try to draw a picture of that. So I have this and that. Okay, so this is I don't know how to describe this region. I guess it's like a tube, but it's kind of flared at one end. Okay, it's not wildly important what the object is, just to help you see it. Sometimes it helps describe it. Okay, so I revolve this region around the x-axis, and again, my typical slice, which I'll draw in green at the point x, looks like this. I have an outer circle, and I have an inner circle, and the slice is the area between them revolved around the x-axis. Okay, so pulling it off to the side, like that same view from the origin looking down the x-axis looks like this. So it's not a disk anymore. It's a big disk with a little disk taken out of it. It looks like that. So you might call this like a ring, or a mathematician might call it an annulus. We're going to call it a washer for this class. So here's the center. That's where the x-axis would pass through this picture. And so in order to find the area of this, I need the outer radius. The outer radius is given by, let's draw it in blue. The outer radius is this distance. This is f of x, right? Because that's the larger of the two functions. And the inner radius is this distance, and this is g of x. So how do I calculate the area of this two-dimensional object? I take the area of the larger disk, so a of x, the area of the larger disk, which is pi times f of x squared, and I subtract the area of the smaller disk, pi times g of x squared. Okay, and then this is the area of each slice as I'm moving from A to B. And so to find the area, to find the volume of the entire object, I just integrate this function from A to B. Okay, let's go over that one more time. So the cross sections, we call them washers. They have outer radius, whichever function is bigger, we call that f, and the inner radius is the smaller function. And so the cross-sectional area is pi times the outer radius minus pi times the inner radius. And then I can compute the volume by just integrating this from A to B, and I get this expression. Okay, so you can go and memorize this formula, or I think it's better to memorize how we got the formula. It's not that complicated as long as you remember that you can compute volume by integrating cross-sectional area, then computing cross-sectional area each time isn't that bad. Okay, let's do an example. I want to take the region between y equals x squared plus 4 and y equals 2 over the interval from 0 to 2, and I want to revolve that around the x-axis. That gives me some three-dimensional solid, and then I want to find its volume. So go ahead, pause the video, try to solve this problem, and then we'll go over it. Okay, so I always want to draw a picture first. You don't have to if you have a particularly good idea for what this looks like in your head, but I don't pretend that I do. So here's this. Okay, so this is the x-axis. This is the y-axis. Here's the line y equals 2. And then x squared plus 4, going from, here's 1, 2, x squared plus 4 starts, the value of the function at 0 is 2, and then by the time I get to x equals 2, I'm at 8. So once again, I've not drawn my picture to scale, but it's not that important to have drawn it to scale. So here's my region. So this here is y equals x squared plus 4. And I'm taking this and I'm revolving it around the x-axis. So here's my little revolving symbol around the x-axis. And the way I draw these, you've noticed, is I draw the region in where it is in the I guess in the first quadrant here, and then I draw its mirror image this in the fourth quadrant. This helps me kind of get a sense for what the solid looks like, because then I draw these circles, which helps me visualize the object. I don't know. If it doesn't do anything for you, then maybe don't draw these extra circles if it makes the picture too busy and confusing. Okay, so once again, here's my green slice at the point X. It is going to be a washer. Looks like this. Oops, let's go like that. Okay, so here's my washer. And its outer radius is the function that's on top in my original picture, which is, so the outer radius is the function that's on top, which is x squared plus 4, and the inner radius is 2, right? It's just this horizontal line, which is always, for every x, the inner radius is always 2. And so from this, I get that a of x is pi times the inner radius, sorry, the outer radius squared, minus pi times the inner radius squared. I guess I can simplify this a bit before I put it into an integral. I have pi times x squared plus 4 squared is x to the 4th plus 8 x squared plus 16, and then I'm subtracting 4. Okay, so the volume, remember, is always just going to be the integral over the interval that we are working over, which is 0 to 2, and I have pi times x to the 4th plus 8x plus 12 dx. Okay, so I intentionally didn't leave enough room for me to do the integral here, because this was all I really wanted to illustrate, okay? Setting up the integral for these problems is usually, I mean, almost exclusively the hard part of the problem. Actually, evaluating the integral is secondary. So I'm going to say I'm done with this problem. I mean, you should, by yourself, evaluate this and see what it is, just for your own education and practicing evaluating integrals. But here, the whole point of this lesson is setting up the integral correctly. Okay, so we've talked about using disks and washers to find the volume of a solid of revolution. We're going to have one last exercise where we're going to revolve the region around a different axis than we have been. So previously, all of our axes of revolution have been the x-axis. In this problem, you have to revolve a region around the y-axis. So pause the video and give it a shot, and then we'll go over it. Okay. So I'm revolving around the y-axis. The region is actually the same region from, I think, the first exercise. That might not be enough room. So here's 1 and 2, and here's y equals x squared. Here's the point 2 comma 4. Okay, so here's my region. Oops. But now I'm revolving around the y-axis. And so here's that mirror image picture. Guess it goes over here. Okay. Okay, that's going to be good enough. All right, and so my solid revolution is kind of like a bowl. And once again, here's the typical slice. So now, hopefully you can see I'm revolving around the y-axis, meaning my slices are going to be perpendicular to the y-axis instead of the x-axis. So I'm looking at the slice at a height y on the y-axis instead of at the point x on the x-axis. So it's still a washer, but again, you have to flip your perspective from thinking about everything in terms of x to now thinking about things in terms of y. Because I'm revolving around the y-axis, and for the washer method, all of our slices are perpendicular to the y-axis, and so everything needs to be in terms of y. So it will be useful for me to write this, the equation that we used. We should solve it for x in terms of y. So here x is the square root of y. We can take the positive square root because we are looking at this part, which is in the positive x side of the plane. Okay, so here's the washer. Let's draw it. Here. You don't always have to draw the washer. I'm just doing it to illustrate. All right, so here's this point here is the y-axis, and so what is the outer radius? The outer radius is the distance from the y-axis to the outermost point. The outermost point is the line x equals 2. So here's the outer radius. This is always 2, independent of y. And hopefully you can see that the inner radius is the distance from the y-axis to the curve here, right? And it's not x squared because we need things to be in terms of y. That's why I wrote x equals square root of y. So the distance from the y-axis to this curve in terms of y is square root of y. Okay? So now that we have this setup, we can write down the area of the cross section at y. So a of y is the outer, the area of the outer disk again, which is pi times 2 squared, minus the area of the inner part, which is pi times the radius is square root of y, and then we're squaring it. So that's just pi times y. So we have 4 pi. Well, actually, we can write it as pi times 4 minus y. And so we find that the volume is given by this integral. We're integrating not from 0 to 2. This is misleading. We're integrating along the y-axis, and this solid extends from y equals 0 to y equals 4. So we have 0 to 4 pi times 4 minus y dy. And okay, so you can evaluate this integral on your own and you find the volume. Okay, that's the basics of volume of revolution. They can get more complicated. We can take axes that are not the x-axis or the y-axis, and then you have to be more careful about what your inner and outer radii are and which functions you should actually use, like we did here. But I advocate always for drawing a picture, right? Like the first thing that you should do when you're solving one of these problems is draw a picture and get a sense for what's going on. And then you can usually figure out what the area of the cross section is just from your picture. And then you don't have to memorize any formulas. Okay, that's the end of this lesson. I'll see you next time.